And good morning to you, everyone. It's my absolute pleasure to be back here today with you for another 3 hours of quantum physics. I noticed after the lectures yesterday we had quite an active chat, and some of us had some interesting discussions on Twitter. So looking forward to day 2. Let's get to it. What's on the road ahead today? After reviewing some of the main takeaway messages from yesterday, I'll dig into the details of what is the Transmon qubit, how exactly does it originate, and you notice that all of the things we spent diligent due time on yesterday, understanding the harmonic oscillator, will very naturally extend into the world of nonlinear or anharmonic oscillators. The harmonic oscillator really serves as a founding basis for so much of physics. So that's why I wanted to make sure that we spent some good time reviewing it so that everyone can really get a both detailed but also intuitive sense of how it works. Recalling the quote by Henri Poincaré. And today we'll see that the Transmon qubit isn't too far away. We're actually only 1 or 2 steps away conceptually from understanding how to create the qubit, how to even calibrate it, as well as how to take advantage of some of its higher excited states. That will lead us into the next step, which is on the control of the qubit. And I think a lot of you have already gone quite far in discussing the lab, which is a very deep dive into qubit control. And here I'll try to give a bit more of an overview of the conceptual ideas, as well as grounding some of the core features of that physics in some of the math of quantum equations. After that, we will take a leap into discussing how is all of what we learned related to actually reading out the qubit, because nothing lives in Hilbert space. At the end of the day, you always have to communicate between the world, the macroscopic world in which we live, and the somewhat abstract unitary operations, gates, and so forth that we perform in a quantum computer, and the link is measurement. And how is that measurement exactly done? We'll see that in our superconducting quantum systems, that's carried through using a type of oscillator, and we're back to oscillators. So you'll see that coupling a Transmon qubit to an oscillator can allow us to do a very beautiful projective measurement of the z quadrature of the qubit. And that is exactly how all the experiments you might have run in Qiskit run. Going into more detail, also if you've touched on things like Qiskit Pulse, you notice that measurement is a very rich and deep field of its own. And we'll really dive into some more details on how do I now look at the coupling between the qubit and its measurement apparatus, the readout cavity, which mediates the interaction between the observer, the bath, and the quantum system at its core, the Transmon qubit. And that will lead us into conditional or pointer states. And finally, as we close out on our road today, there'll be a lab, of course, that follows all of the discussion. Now let's begin with a bit of a takeaway on Lecture 1, some of the core messages that we can take home, and then build on. I love this quote by Asher Perez. Quantum phenomena do not occur in Hilbert space. They occur in the laboratory. And I hope that given the discussion yesterday, you saw that a lot of what I hope we can achieve here is to both focus on the description of the phenomena as much as on their physical character and providing a mental picture. I think it was also Pauli or Heisenberg who said that we can conceive of so many great things with our mind, but not necessarily always immediately understand them mathematically, but often it's the heuristics that leads the discovery. And that leads me to maybe the first slide, which is an overview slide of the connection between where you sit today at your laptop computer and the abstract Hilbert space, which you control and manipulate and can experiment on in the real devices. And the link between these two is formed by the following chain. You might send some sort of encoded information, as a Q object for instance, from your laptop into a laboratory. This laboratory contains a superconducting, or rather a dilution refrigerator with some control electronics around it, which houses the golden chandelier. And there were some interesting questions yesterday, which I think are summarized, have answers summarized in the Discord channel that discuss why it's actually golden and why that's really important. However, the quantum chip sits at the very bottom of this dilution fridge and often looks something like this, where each of these two metal pads connected by some sort of nonlinear inductor form a Transmon qubit. Now all the squigglies between them are, take a guess, more oscillators. Our bread and butter ingredient. Hence you can tell my love for oscillators. The Transmon qubits can be connected by oscillators as well as these extra oscillators that sit on the outside, which are readout oscillators or resonators. We can model these using lumped element electromagnetic circuits, which form a very beautiful bridge between simple classical physics you might have started learning about in high school and opening the door into unveiling the quantum world, in which the rich character of quantum oscillators and nonlinear quantum physics and quantum optics can be exhibited, and they form an amazing testbed for both academic research and industry applications today. The oscillators, of course, provide us with a submanifold of the larger space of the oscillator, which we use as the qubit two-state manifold, or which we can represent in the block sphere, which you learned about in the first week of the Qiskit Summer School. Now, to make a more concrete connection, yesterday we drew this picture of a Transmon qubit connected by two metal pads and a little wire between them. This wire is usually a nonlinear, so-called Josephson tunnel junction. The amazing thing about almost all of this is that you don't really necessarily need to know a whole lot about the details of the superconductivity here. You can take that as an abstraction and really focus on some of the physical effects of what are the charges, what is the charge doing as it flows across, and what is the magnetic flux doing, which is related to either the integral of the voltage or the magnetic field lines. And we saw that both the Transmon qubit and the readout oscillator will all have a simple phenomena of the sloshing of the electric fluid of charges back and forth between different regions in space, which are associated with time variations in the charge and flux, and because of the capacitance and inductance of these circuits can create very specific types of oscillations. And in the quantum world, in the world of low dissipation, in the world of some nonlinearity and low temperature, we can begin to find that the energy spectrum of these oscillators is quantized, that you can create coherent superpositions between them, that if you take two of these transmons you can create entanglement, you can create logical gates, and so forth. And that led us into an interesting discussion of the quantization of the harmonic oscillator, which I emphasize again is the bread and butter to understand before leaping into all of the next subjects that we will do. The harmonic oscillator, of course, has a quadratic dependence in terms of the position variable, which we identified as flux. So this parabola here is the potential energy, which goes like phi squared over 2L, where phi was the integral of the voltage with respect to a reference state from, we call it time minus infinity, but it's just some initial reference state. It's mostly a label. It could be t0 to some time here. Now the important thing is that when we quantize this oscillator and move into more of the quantum world, we can notice that the harmonic oscillator has energy levels that are spaced exactly by energy h bar omega naught. where omega naught is the resonance frequency of the oscillator, the very familiar 1 over the square root of LC. So the geometry, through the effective inductance and capacitance it creates, will set the resonance frequency. And as I'll show in a minute, the zero-point quantum fluctuations are also set by both L and C. When we move into the quantum domain, we can describe this quantization ladder of energy states by Hamiltonian that we can write in a basis, the eigenbasis of the Hamiltonian. And I call these Fock states. There was some number of questions, I think, yesterday about what exactly do I mean by Fock states. And sorry, when I write n here, I mean that this bottom level is the 0 Fock level, the 1 Fock level, the 2 Fock level. Why am I calling these Fock states? Here by a Fock state I mean that I have either 0 photons of energy, which is the ground state in the oscillator. Now that doesn't mean that there's no energy. There is 0 photon particles. That doesn't mean there's no energy. It just means that the oscillator is in the ground state. However, it still fluctuates, as we saw yesterday. The 1 state, it's the first Fock level, or it's the 1 photon excitation, and it's created by the A dagger operator. So 1 is equal to A dagger 0. So we can think of A as the photon creation operator, 2 as the photon creation operator created twice, and so on. So we've put 2 quanta of energy, or 2 photons, inside the oscillator. Good. Now, taking the bridge from the classical to the quantum, I think for me is also one of the next essential elements, and I'm very glad to see that I'm going to assume Bruno here would like that as well. And I think it's important to highlight that even though quantum is fundamentally richer than classical physics, we can still try to gain so much intuition by bridging from the classical world into the quantum world and trying to make us a close analogy between the two in our bridge. Because some things that can be quite difficult perhaps to understand, such as what exactly is the ladder operator, the annihilation operator, and why does it evolve using an e to the minus I omega naught t, can have very simple pictures that can explicate that in the domain of classical physics. We saw that in classical physics we can think of this alpha operator, or alpha variable, excuse me, a complex action angle variable, as a point in the phase space that simply rotates around the circle and represents the harmonic evolution. That's something very simple. However, as we go into the quantum world, all of that gets more complicated or more rich due to the intrinsic uncertainty between position and momentum. We cannot identify in the quantum world the quantum state with a single point in phase space. We can also make the analogy between position and momentum for the somewhat abstract charge and magnetic field. And in our case, we can make the analogy that these quantum oscillators have position, that the magnetic flux that looks a lot like the mechanical position of a spring as the spring oscillates up and down from its rest position, its equilibrium position. The mass goes like the capacitance, and then the spring constant of this spring goes like the inverse inductance. The Hamiltonian in the quantum world can be expressed in 2 different bases, essentially. In the first basis, we write it in terms of the flux and charge operators, which directly parallels the more standard description in the classical physics. But it also has a very advantageous representation in terms of creation and annihilation operators. A dagger A. Now I think there was a question I saw in the discussion box here, which was, why did I drop the 1/2 yesterday? This is a very good question, and it's somewhat subtle, more subtle than it appears at first. Typically in measurements, we can really only measure differences in energy. So in a sense, absolute energy isn't exactly a measurable thing. So you could say, well, you could ignore the 1/2. And if you look at the equations of motion, any constants simply drop out from the equations of motion. However, that's a little bit too simplistic in more general applications, because you can in fact detect the zero-point vacuum fluctuation energy if you do things such as vary the frequency here, or look at more advanced dynamical effects such as the Kashmir effect, which we won't get into today. The eigenstates of this operator are very nicely described in terms of the energy levels, the Fock basis, which we explored in the previous slide, and can have a beautiful representation in the flux basis or the position basis as particular types of polynomials. Here, the different curves are staggered in energy. So the position between the 0th curve and the first curve, or sorry, the wave function corresponding to the ground state and the wave function corresponding to the excited state, which are the blue and orange curves respectively, I've separated by an energy difference of h bar omega naught. And these represent the probability amplitude, meaning that the square of these gives you the probability to find the circuit to have a magnetic flux of this amount. So for instance, the ground state we see is localized around 0 magnetic flux. In the ground state, you don't expect to have any charge or magnetic flux, especially classically. However, we notice that on a time basis, there are fluctuations. So while the mean of the expectation value is 0, there are inescapable fluctuations, which we call the 0-point quantum fluctuations, which give the root mean squared amplitude of the variance, or sorry, of the magnetic flux fluctuating in time. And so these relationships here are going to be very, very key today to determining all of the parameters of the quantum oscillators and the quantum qubits, or the quantum transmon. Okay, and maybe I will pause very quickly and see, Josie, if there are any questions yet.
Yeah, it looks like we have a couple of questions here. I think the one of the most popular ones is how a single IBM quantum computer uses roughly as much energy as 3 hair dryers. And I'm not going to lie, I'm pretty curious myself.
Yes, that's an interesting question. I think, yes, so that's an interesting question. I guess if we go back to the golden chandelier here, let me scroll back. Everything we talk about, I think you remember from the diagram yesterday, all the quantum properties are at microwave frequencies in the order of 1 to 10 gigahertz. So in terms of energy and temperature, these are minute scales. They're very, very little quantities of energies and photons. However, as we mentioned, to work in the quantum world, you have to suppress fluctuations of the thermal environment in which the qubits are embedded. Down here at the bottom, oops, let's get the pen. Down here at the bottom. So we operate at negative 273.114 Celsius. Now, to get to that temperature requires a lot of energy because you have to extract heat from this entire structure. You have to extract the constant flow of heat from the room that the fridge is in. And of course, you need to run all of the electronics associated with the fridge and all of the other pipes and pumps and vacuum systems and so forth. And it's really all of this auxiliary systems that require all this energy. It's not really the quantum computer itself, it's all the auxiliary stuff. And of course, all this stuff is getting more efficient and miniaturizing and getting smaller and so forth. So hopefully that gives us enough perspective there.
Thank you. Sorry, I have to toggle the mute between Zlatko and I, so I'm a little delayed. I'm sorry about that. I think that the next question that looks like a lot of people are interested in is about the qubit electric dipole moment. And you guys can make fun of me. That's fine. I'm just an admin. I'm not a mentor. But they're asking, can we express this dipole moment in terms of the circuit parameters, LC, etc.?
This is actually a kind of a debate in the community that's been going on for some time. Is exactly, should you even talk about the dipole moment of this Transmon qubit? And there are really two views. Although I think the picture has been clarified a lot. You see this Transmon picture here. It looks a lot like I have. Let's get the pen. It looks a lot like I have some piece of metal up here connected to another piece of metal down here through a wire, and you have current going through this wire. So you can try to model this with some, radiation sort of dipole field pattern and talk about its dipole moment. But it's not really in that regime. This Transmon qubit, it's relatively large in terms of the microwave approximation. Say this might be 200 microns across, for instance. And so if you look at the microwave fields, or it's the radiation pattern, if you want, of this Transmon, it has a quadrupole moment and a sixth order moment and so forth, and there are also many different pieces of metal around, so it's not a very pristine picture of a dipole. The picture is much more complicated, and so this is actually where something called the energy participation ratio, which we'll briefly talk about, comes in later, which allows you to bridge this very complicated electrodynamic structure and simplify it through just calculating how much of the energy of this element how much of the energy of the mode, is housed inside of this electromagnetic element, as opposed to all the other magnetic fields around. And so you can talk about an effective dipole moment. The effective dipole moment of the qubit, in a way, is going to really be related to the 0-point fluctuations again, because they will tell us how much current or charge is fluctuating back and forth on average between these two islands. And perhaps it's worthwhile to point out that number is going to be very, very small. On average, you'll see that even though over here there are about 10 to the 12 mobile electrons or Cooper pairs, the number of charges fluctuating across is going to be only about 1, or 1 Cooper pair typically for a Transmon qubit, which is 1 in 10 to the 12. It's a very small fraction, so it looks like a fairly small number, but we can engineer that to be nonetheless a pretty large electric field. So the best thing for now is to think of the size of that dipole moment to be dictated by effectively these 0-point vacuum fluctuations, which are of course given by the parameters of the circuit, the square root of h bar z over 2, where z is the impedance, the effective impedance of the mode here, the square root of L over C. Thank you.
Thank you, Zlatko. I have you muted for just a second. I think those were the two biggest questions, so I can let you resume if you're ready.
Yeah, perfect. And all right. So yesterday we saw that if you look at the phase-space functions of the oscillator, you can you can make a picture of analogy between the classical world, where the energy here, this is, by the way, this curve here represents a paraboloid in two variables, the flux and the charge, this q squared over 2c plus phi squared over 2l. So these are contour plots of constant energy. The innermost one was h bar omega naught over 2, It corresponds to essentially the vacuum fluctuations. The next one is the one photon, and so forth. These are these so-called semi-Q functions of the ground state, the excited state, but basically they're representing that we have a cloud of uncertainty as to where to find the artificial atom or the harmonic oscillator, right? In the one state, you won't really find it in the middle because it's excited, but you'll tend to find it around here. It's very much like the hydrogen atom or any other atom. There was a question which asked, what happens as you go to higher energy levels? So I'll briefly answer that question from yesterday. Essentially, you get a donut. The donut grows. And the radius of this donut growing as you go from the ground state to the first excited state to the second excited state to 3 photons of energy 4 grows like the square root of the energy here, or in other words, this grows like alpha. And we can recall that the Hamiltonian, or the energy, goes like alpha star alpha, or the magnitude of this complex number. Now, with all that introduction, let us move into the Transmon qubit. So what is the Transmon, and how is it different from the harmonic oscillator we've so extensively discussed so far? It's surprisingly similar because the only thing we're going to change is this element in the center here. Rather than a linear inductor, we're going to replace it with a nonlinear inductor, the Josephson tunnel junction. And this is what a Josephson tunnel junction looks like in practice. Many thanks to Luigi Frunzio here for this image he's taken from some time ago. What you see is a microscopic image at the order of about 100 nanometers across. This is very, very, very small. And so this is one piece of metal that you see in this picture here, which has a width of about, say, 200 nanometers, right? This is really nanolithography. Then there's another piece of metal over here, which also has a similar size. And the two pieces of metal fall on top of each other. We see that if I take a cross-section picture over here, there's the bottom piece of metal, and then there's the top piece of metal. Now, between the two, you notice that there is a ridge, or not a ridge, but rather there is some sort of barrier, an oxide barrier. If it doesn't even matter, actually, what the details of this whole structure are. The important thing is that however it's formed, this weak link between these two superconductors establishes a beautiful relationship between the two terminals, which I might label as, say, terminal 1 and terminal 2. And we can describe the element by a potential energy function, or an energy function, which only depends on the change of magnetic flux across the two terminals and nothing else. Even though you can see that the picture on the right is very messy and there's all kinds of little pieces of metal floating around and a lot of things are happening, we can ignore all that detail and just very robustly abstract it away into a nonlinear inductor, an inductor that has a potential energy function that looks like this, where the potential energy of the Josephson junction, so I've included an index J here to denote Josephson junction, I'll suppress it in the next slide, depends on the flux difference across its terminals, is given by some energy scale, which we'll call EJ, the Josephson tunneling energy, and 1 minus the cosine of the flux scaled in terms of phi naught. Phi naught is the reduced magnetic flux quantum. It's a somewhat universal constant, and has a very small value of about 10 to the minus 16 Webers. Now, if that looks a bit complicated, I agree, we can actually break it up into two pieces. Let's simplify it. Let's break it up into a linear piece, like harmonic oscillators, plus a nonlinear piece, which can quantify the amount of nonlinearity. So if I separate it out into two contributions using a Taylor series expansion and dropping constant terms, we can see that the cosine breaks up to first order into a quadratic term, which goes like the magnetic flux squared over phi naught. times EJ. And this is nothing but the energy potential landscape of a linear inductor. Remember, phi squared over 2L. This phi squared over 2L allows us to make the identification that the effective inductance at zero bias of the Josephson tunnel junction is related to EJ. Or if we write it, let's delete that and write it a bit more clearly and say that we can make the identification that EJ divided by phi naught squared is equal to 1 over LJ. Or in other words, the Josephson tunnel energy is equal to phi naught squared, where that's the reduced magnetic flux quantum, divided by LJ. And so we can really link the expression for the Josephson tunnel energy, which describes how easy or difficult it is for electrons to, or Cooper pairs to tunnel across these two islands, to a linear effective inductance. Now the nonlinear part is what we haven't yet seen, and that's going to really provide all the magic for all of the Transmon qubit, the amplification, the coupling to the readout, and so forth. And that's a quartic function. It depends on the fourth power here of the flux. And it has a coefficient of 4 factorial, which is 24. There are also higher order terms which go like the magnetic flux to the 6th power. We can ignore those because we'll see that the overall contributions here will be pretty small of the nonlinear piece. In other words, we want nonlinear oscillators, but we don't want them that nonlinear that they're too difficult and to control. And we can symbolize the purple part, which represents the nonlinearity, with the quartic nonlinearity, with one of these symbols here. So let's look at the Transmon qubit from the same viewpoint which we use to look at the harmonic oscillator. The Transmon qubit has a potential energy function that looks like negative EJ cosine of phi over phi naught. It's a funny cosine potential, and it has the exact same capacitive energy function as a harmonic oscillator. Now the magnetic flux quantum, to remind us, is h bar over 2e. So you see that it's very fundamental. It's formed from two fundamental constants of nature: Planck's constant for the quantization of energy, or the quantum of action, and the electromagnetic charge of a single electron. There's a 2 here because we're talking about superconductivity, so we're interested in pairs of electrons. And it has a value that's very, very tiny. A Weber is the unit of magnetic flux. The potential energy landscape associated with the cosine looks like this, where on the bottom axis here you can write out the reduced magnetic flux across the Josephson tunnel junction. At the center it's 0, and it's periodic in pi, or in here, in 2 pi. And we have the classically forbidden region, which is where a classical particle can never be found or live at a given energy, shaded out in gray. The cosine is represented by this oscillating potential, and the energy goes between here, negative EJ and positive EJ, because I've dropped the constant term in the energy. Now, somewhat crucially, we can make the following approximation. We can approximate the potential energy landscape of the Josephson junction to first order as a quadratic, the linear inductance. And so in this picture, it looks like this purple parabola here. A striking thing emerges, which is that the parabola and the cosine are very similar. They're not very different, actually. If you notice, especially in the limit of low excitation, in the limit where the junction isn't highly excited, but we operate near zero magnetic flux, you notice that the difference between the purple curve and the gray curve here is almost indistinguishable. And we're going to use that. We're going to heavily, heavily exploit that. So here is the classical Hamiltonian of the Josephson tunnel junction. if we apply the same semi-classical intuition as we did for the harmonic oscillator, we can quantize its energy in say, units of equal photon number. Now that's actually going to be wrong. We should be quantizing the action, but I won't get into that subtlety since we'll see that the pictures are fairly close. And writing out this this equation here on a 2D plane in terms of the position variable phi and the charge variable or momentum variable q, we can see that the contours of constant energy represented by these paths over here, which represent the classical trajectories that a particle will experience, start out fairly circular and then elongate as you get to higher and higher energy. Higher energy is indicated by the brighter spots in the region. So the dark spot here is sort of the deepest part of the valley. You can think of this as a mountain range. So up here, if you're a cartographer, you'll notice down here is very low, and each contour tells you that you've climbed up by another 100 meters if you like hiking. Here we can identify the superconducting, the magnetic flux point. Let's say that the particle of the transmon starts here. Classically, it's described by a point. The trajectory it follows as a function of time is no longer a circle but an ellipse. And that will lead to this strange nonlinear behavior. In the quantum world, we simply will put hats on things. Now, formally, we follow the exact same procedure for the classical circuit, where we write down the Lagrangian and do a Legendre transform to go to the Hamiltonian by identifying the canonically conjugate variable q, and then we apply Dirac's quantization procedure with the commutators, but really nothing at all at this point has changed between what we did yesterday for the harmonic oscillator and for the transmon. The only thing that's changed is the potential energy function. However, it doesn't affect in any way any of the steps we took so far, because the basis we chose was to use the position variable as the magnetic flux, and therefore in identifying the canonically conjugate variable to that, we didn't need to worry about changing anything about the cosine. That's a maybe more subtle detail for the physicist in the audience. If we expand the Hamiltonian in the quantum world into a linear piece and a nonlinear piece and drop terms that are higher than fourth order, we can again effectively approximate the potential energy landscape here using the quadratic part, which is this purple curve represented by the q squared and phi squared, and then we'll take kind of the next order approximation between the purple and the gray. If you remember from the harmonic oscillator, we can exploit the fact that the beginning of part of this Hamiltonian, or the start, is just a harmonic oscillator, something very near and dear and familiar, right? We can exploit its solutions that we found in the first part of this lecture as an efficient basis in which to describe the nonlinear piece formed by this second potential energy function here, which I'll call H nonlinear. And if we use the simple harmonic oscillator solutions, you'll recall that several times we wrote down the position operator. Phi is the quantum zero-point fluctuations of the flux times A plus A dagger. Now we can plug that into this equation and define a reduced variable, which I'm running out of space here, but let's write it as lowercase phi ZPF, which is simply capital Phi ZPF stripped of its capital status by the reduced magnetic flux quantum. And for definition, I'll use this asymmetric equal sign symbol with two dots and an equal sign. You notice that also in moving from this from the box line to the next line, I've made the substitution of replacing the linear part of the harmonic oscillator in terms of the annihilation and creation operators A, dagger, and A, and replacing the frequency. So everything we saw about the harmonic oscillator so far is simply a plug and play into this slightly more non-harmonic equation, anharmonic equation.